Welcome to the lunch and dinner session. So the first speaker is Joel Moore. So go ahead. 20 minutes plus questions.
I'll do my best. So let me thank the organizers in particular for their commitment to making this a success in challenging circumstances. I feel like I've already learned a lot scientifically. And what I'm going to talk about, I think you will see rapidly connections to Tomasz Prosen's talk earlier today and also to Professor Bushul's talk earlier in the week. So I'm going to talk more about these unusual properties of one-dimensional dynamics and focusing on how at least one aspect of the KPZ universality class, namely the Z equal to 3/2 superdiffusion, does seem to be visible in solid state experiments, which was a pleasant surprise. So I will give a little bit of background on I guess some simpler cases and then a little bit about KPZ, but I think as already came across, KPZ is a very new idea in this context and people are still working out various aspects, but there has been an enormous amount of progress in the last 2 years. Even though I'm a theorist, there will be some experimental strong component in this talk, be forewarned. All right, so very quickly as motivation, since you've already heard about this, it turns out that even though we've known for a long time that one-dimensional systems are especially tractable, even when they are in the thermodynamic limit and have a large number of particles and so on, the first paper I'm going to talk about is just to review quickly, and I'll talk about some of the older history as well, of course, but this slide is just our papers if you want to read more. Why are there new kinds of hydrodynamics in one dimension? What does that mean? And how these sort of integrable models in particular fit in between what you could view as the various other possibilities out there for how things move around, depending on conservation laws. So the special case here is, of course, that they have an infinite number of conservation laws, but the importance of that for dynamics was really not understood as well as it should be until 5 or so years ago. So the next question is, does that actually matter in an observable sense for matter that we can measure in the laboratory? And you've already heard about one case of that in this conference. What I'm going to talk about is basically, I guess I'll first show some numerical evidence that led us to conjecture something that there have been steps toward proving, as in Tomasz's talk, which is that it seems like if you have a combination basically of integrability and some notion of isotropy or non-abelianness, roughly, then you do get this unusual superdiffusive behavior. The numerical evidence for that is in the first paper here. The second paper here, the story is basically going to try and convince the oldish folks who did the neutron scattering on spin chains back in the old days to see spin-ons, that actually they missed something. We thought that might be more impressive if we could convince them than if we went and found new people. But they were good sports, and the main point is you can see a regime which is not where we normally look at neutron scattering on spin chains, but where there is good evidence. I would not say an absolute proof, which is hard in experiment, especially on solids, but there's good evidence for Z equal to 3/2. And then the last paper here, which just got online published in PRL today, in fact, is understanding how to reconcile the sort of high temperature limits of KPZ with the low temperature limit that we all know about of Luttinger liquid type physics. All right, so this next part I'm going to go through very quickly because I think people here know it well. So standard physics of many particles tends to depend on equilibration to a Gibbs ensemble. We know that there are exceptions. So MBL systems, for example, certainly don't thermalize in a conventional way, no matter how long you wait. But another possibility is that maybe there is a notion of equilibrium, but it's different from the one we normally think about because there are extra conservation laws. So instead of the Gibbs ensemble, we have the generalized Gibbs ensemble. And turning that into a practical machinery to calculate how things move around was maybe the recent progress. So very briefly, much of what we do depends on the assumption that things relax and in a way that gives us finite linear response coefficients, finite diffusion coefficients, in the original example due to Einstein. There's a whole philosophy of how returning to equilibrium from a spontaneous fluctuation is the same ultimately as returning to equilibrium when you're pushed away. So a whole lot of standard physics is built on diffusion. This talk is mostly about two kinds of exceptions to diffusion. But just as a reminder of what you would expect, probably if you waited long enough in any real solid with phonons and all the other complexities, you would expect something like a diffusion constant where you do have a conservation law, number of particles. Let's just talk about particle number as the simplest case. And then if we started with a narrow peak in the number of particles, that would spread. It would be a broadening Gaussian is a solution of the diffusion equation. And the way we translate that to a magnet is, well, in a magnet, let's say that the total magnetization is conserved because of the symmetries of the Hamiltonian. Let's assume that. Then the sort of zeroth order guess is that the magnetization density will behave in the same way. And that is a dynamical exponent of z equal to 2. So this is what experimentally you might expect to see a lot of the time. Like if you had a dirty crystal with a lot of momentum relaxation and scattering, this would be your best guess. So where things can become different, we know that the number of conserved quantities in a system and whether there are more than one affects whether you get diffusion or other behavior. So for example, the behavior of water and air is not diffusive in general because it's described by this more complicated set of equations. And this is in the simplest limit, zeroth order hydrodynamics, because there are three conserved quantities. There are three of these equations. And so now you could ask, well, if I had an infinite number of conserved quantities, would I have to solve an infinite number of equations? And the magical fact is no, not really. But you can derive all these through a sort of reduction of the Boltzmann equation. And maybe the key physics point is that the Boltzmann equation in standard fluids has a lot more information than these three hydrodynamical equations. The Boltzmann equation has the full one particle distribution function. These three equations on the slide are only about 3 integrals over that. So hydrodynamics is ultimately the problem of how local equilibrium becomes global equilibrium. So I'm going to talk about the one-dimensional spin chain, and in particular the XXZ spin chain for this talk. So there's the Hamiltonian, which you've probably seen before. It has a lot of conserved quantities. This is from a paper of Prosen. And the main point is, we need some practical way to deal with these enormous lists of conserved quantities. So to do that, it turned out, in fact, that half of the conserved quantities, the sort of odd ones, had been missed for a very long time, for at least 40 years. That was understood starting in 2011, and one can, once one has the new conserved quantities, it starts to become possible to answer a lot of questions about dynamics that were not possible before. So even though Bethe solved the ground state of this model in 31, and the thermodynamics were done in 1970-ish, it seems like every 40 years something interesting happens, and we're still, I think, in that interesting period from 2010 or so. All right, so I'm going to come back a bit to what happened between 2010 and 2019, but first, this paper by Ljubotina, Znadaric, and Prosen was very exciting, I think, to people in the field, and I'm going to talk about experimentally trying to see something related to what they proposed, or what they observed, which is that at infinite temperature, at the Heisenberg point, in other words, the point where the X, Y, and Z couplings are all the same, you don't see diffusive behavior. You instead see a kind of behavior both in the exponent and in the scaling function. And we also, we reproduce this after the fact. We agree with what they said, that the sort of noisy Burger's equation, or a nonlinear version of diffusion, gives rise to a behavior that is faster than diffusive behavior, but slower than ballistic behavior. That's equal to 3/2. So as a quick picture, this is what I mean by saying the blue curve is not spreading as rapidly as a ballistic system, but more rapidly than a diffusive system. And this appears all over the place in classical physics. I would say this is almost the first occurrence I know about anyway, in a quantum coherent system. Why, as you've already heard, is still sort of being worked out, but parts of it can at least be shown, and I'll give a reference later on. So I'm going to skip a little bit of the background on but yeah, maybe this is a good slide to show, to give credit where credit is due. So a lot of the, when I said 5 years ago, interesting things started happening, a lot of that is in these two papers. I'm going to talk about a way to understand what happens in the ballistic case first, because that was done a few years ago. And that will lead us now to the Heisenberg case, where things stop being ballistic. So in general, this XXZ model has a ballistic regime when it's when it's easy plane. It has a diffusive regime when it's Ising-like, easy axis. And at the Heisenberg point, that's where you might hope for something in between, but you would have to be very clever to hope that what was in between was this KPZ universality class. All right, so the basic idea of those papers, which has actually occurred before in classical physics, when you think about like many solitons. So integrable classical systems have the same kind of equation. And the way to think about it is that in either classical integrable or quantum integrable systems, the way quasi-particles move is that even if you've got several of them coming together, they don't randomize momenta. They ultimately pass through each other, but there is a delay or a phase shift in quantum mechanics. And that means that the effective velocity of one particle depends on the density in momentum of all the other quasi-particles at the same space-time point. So it's like a Boltzmann equation, except that the velocity is a kind of integral itself. So it's an integral differential equation, but we now understand various cases of how to solve this either analytically or numerically. And it's really quite powerful. And I'll try to convince you that it's powerful in the ballistic case. But just by staring at this, it's not at all obvious that something interesting is going to happen when you go to the Heisenberg point. But very briefly, so this is the picture I just described, that where this equation comes from, and it's actually equivalent to that infinite hierarchy you would write of Euler type equations, is that one soliton moves through another, for example, and I think this is for the classical nonlinear Schrödinger equation, but there is a time delay. Quantum mechanically, we know that in integrable systems, it's not that particles are free, they have phase shifts when they scatter, but those phase shifts are like a delay in semi-classics. So the surprise is not that everything is captured by semi-classics, but a lot of things are captured by this effectively semi-classical Boltzmann type equation where the quantum mechanics just went into that self-consistent velocity. So the neat thing is this gives you a whole recipe to solve a lot of problems, because now you have a recipe to get from sort of local generalized Gibbs ensemble, which we think sets up quite rapidly. It sets up on the scale of a few collision times in general, but then the very long sort of streaming time scales, how you evolve on the manifold of GGEs, that's what's given by these hydrodynamical equations. And this even works, not just for kind of one variable x over t scaling limits, but it's a remarkably good approach for the long time x and t limits. And just to kind of convince you of that numerically, this is a talk from 2 years ago maybe, but these are pictures comparing what you get by microscopic DMRG simulations and from those hydrodynamical equations. And you can find cases where they lie right on top of each other, and there are small but measurable deviations from what some, say, ordinary hydro would give. So this is, if you like, a check on both, because they're making totally different approximations, but neither one of them seems to be very approximate. This is for the XXE model at delta of like 0.5, so reasonably strongly interacting. All right, so now let me finally come to this gapless point, the KPZ equation. And then, to try to fit everything together and go to finite but not infinite temperature, the point of this paper, and also studying a lot of other spin chains, so I won't show everything because the only experiment I have to talk about is the good old Heisenberg spin half chain. But the point is, you do get 0 Drude weight, no ballistic transport, but an infinite diffusion constant. It's this intermediate behavior that is superdiffusion, and the conjecture, which there's now a lot of evidence for, is that that depends on the combination of integrability and a non-abelian symmetry, if you like, which in the spin case is a form of isotropy. All right, so, and I wanted to mention in particular, there are Lieb-Liniger type atomic experiments that fortunately you already heard about in this conference. Those are very beautiful by Bushul and Dubai. I'm going to talk about the Heisenberg point. So those tend to be in those are experiments that you would have to tune a bit to get to the Heisenberg point. The nice thing about solids, there are many not nice things about solids. They're three-dimensional, you've got backgrounds and so on, but that you can be naturally tuned to the Heisenberg point basically by the cubic symmetry of the solid. And then, yeah, I think I'll skip the second comment there. We have thought a lot about broken integrability. So the point here is this is an actual crystal that was used in the old days to kind of establish that you could see spin-ons in an actual material, potassium copper fluoride. It's very well described by the 1D Heisenberg model, unless you go down to low enough temperature that the 1D chains start to talk to each other. So below 25 Kelvin or so, it becomes more like a three-dimensional material. But a great thing about this KPZ physics is that it's really not a low temperature phenomenon. It's a moderate or high temperature phenomenon. But of course, in a real solid, you'd worry that as you go to high temperature, eventually you melt the crystal. And before that, you produce a ton of phonons, and the electronic system is not really a closed system. So I think the reason for doing the experiment is to ask, is there a window of time that you can observe where the physics is not ballistic and not diffusive, but this intermediate behavior? And in particular, when I say that people didn't really look for this in the old days, this is not contradicting something from the old days. It's that people normally would look at high energy and low temperature and try to resolve this kind of spin-on physics. And they would also tend to look near Q equal to pi. This talk is really about mostly near Q equal to 0. And it's about the opposite limit of frequency and temperature. It's about high temperature and low frequency. So in other words, long time limit, but hot enough that the system is really not in its low temperature limit. Things have time to interact and do interesting stuff before they ultimately become diffusive as you go to higher and higher temperature. So the particular thing we're going to do, let me maybe, I think in the interest of time, skip over some of this. There's the crystal structure on the left, and we're going to measure the standard neutron scattering observable, integrated over a window in frequency, and ask, does that scale with wave vector q? And the black curve here are numerical simulations. And there's only one sort of number to get out, which is what is the scaling with momentum? And we sort of know, because we've defined a window of finite frequencies, it's hard to go too low with neutrons, too high, and you would hit other physics aside from the point we care about. So there's certainly only 1 decade of scaling. But you can say that until you get down to low temperature, things get complicated. There's 3D crossover and other issues, but there's a pretty broad range of very easy temperatures to work at, from say 150 Kelvin up to 300 Kelvin, when the fit is much better to KPZ behavior, or at least, let me be precise, the fit is much better to z equal to 3/2 than it is to z equal to 1 or z equal to 2. The values are, say, in a range of 1 1/3 to 1 1/2 plus a little bit. And it is a nice success of, by the way, one-dimensional numerics at finite temperature. So if you plot the data in the right way, you can really see that these matrix product state simulations or DMRG are computing something. And the key is, I think, most clear in the bottom right figure, that you can draw a pretty good line through the points even at room temperature. So that is really a regime for quantum dynamics where we wouldn't have thought to look. Normally we'd say, go look in atomic systems so you don't have to worry about phonons, and go look at low temperature to remain coherent. And maybe the surprise to me, which I like, and the paper is out in Nature Physics a couple of months ago, so this reference is old. I guess the surprise is that there is quantum coherent dynamics of a very interesting category that you can start to see nice signs of even in a real 3-dimensional solid at 300 Kelvin. And I think that's the main point I wanted to get to in my 20 minutes. So if I can have 1 or 2 more minutes, maybe I'll add a couple of other implications of that. And the main one is just how does that fit together with what we learn in school, maybe about how to approach these spin chains theoretically? So there may be 2 things you learn if you care enough about one dimension. You learn how to solve them for the small number that are solvable, which is through the beta ansatz. But then maybe the other thing you learn is that even for spin chains that are not exactly solvable, there's a very useful tool, which is sort of Luttinger liquid physics and bosonization and things like that, which is that for the gapless phase up to the Heisenberg point, but including the Heisenberg point of the spin chain, there's a very nice way to look at it as free bosons. But now all of a sudden you have a problem, because free bosons are z equal to 1. They don't look a lot like z equal to 3/2. So something about that low temperature physics has to cross over as you raise the temperature or wait a longer time or look at a different length scale. So the point of this recent paper is to try to understand how, as a function of space and time, do you cross over between these 2 regimes. As you lower the temperature, you start to see the Luttinger liquid physics, although it turns out you have to go to really rather low temperature and rather long time scales because of some prefactors being small. But the nice thing is there is quite a broad range where you get an onset of KPZ hydrodynamics. And as a general rule, the onset is not some terribly inappropriate scale. It's just like 1 over temperature. I won't try to go into all the spatial dependencies and things like that, but this is sort of a plot of what this looks like in the autocorrelator, that you can see that t to the minus 2/3 behavior setting in for a bunch of different values of temperature. And the paper is basically systematic analysis of how far do you have to go before you start to see KPZ, say, in the autocorrelator and other quantities. So just to kind of conclude, the main point I wanted to make is that, I think the ballistic side of things was understood a couple of years ago, and it's great that there are experiments on that from the atomic end. The Heisenberg point, I think the action really started with that 2019 paper I mentioned, and now there is experimental, realization of that in a place where you might not have thought to look. So as far as what's been going on with theory in the meantime, and let me point out that with neutrons there is no easy way to see the full KPZ spectral function. You can do other things, you can change temperature, you can add a magnetic field. We're kind of trying to do that, but it's hard to get a strong enough magnetic field to perturb the system enough. So experimentally, one thing we're trying to do is to get other spin chains that are, say, more on the gapless side and confirm that things are different. It's very easy to find things that are diffusive, but can you find something that is ballistic over a time scale? But yeah, maybe the good news is if you choose the right material, then you can have quantum dynamics for a surprisingly long time, and neutron scattering, even at high temperature, is a good tool because it can get to low enough frequencies to see collective behavior, not just single spin-on physics, say. So I think this has already come up, but I'll just repeat some key facts about the theoretical understanding. So there's an increasing understanding of which spin chains probably have the KPZ universality class behavior. To be precise, I think there's an interesting distinction here, which was Vedika's question earlier. I think this paper by Ilievsky et al. Basically proves that Z equal to 3/2 obtains under certain assumptions about having an integrable system with some greater symmetry than just U1. And you heard about sort of a different approach to finding other systems that have this KPZ universality in the talk by Prosen. The full KPZ scaling function is hard to compute analytically. We can see it in DMRG, so we can confirm the observations of Lubotina et al. It is also very hard to see experimentally at the moment, but maybe someone will find a way. And then I think, when I say it isn't yet proven, I think there are nice ideas out there, and I think they're probably right. It's just, less than a detailed microscopic calculation, but I wouldn't make it seem like it's totally not understood where KPZ might come from. So I thought I would mention, there are other papers now, but I thought I would start with what was the first as far as I know, which is by Bolchandani. Okay, so with that, I'd like to thank all the people we worked with, both the experimentalists at Oak Ridge. Alan Shea is a postdoc. Alan Tennant and Steve Nagler are very accomplished people in the world of spin chains and ladders. In my group, my current students are Tessa and Nick. There's Nick. And postdocs, Maxime Dupont was really the hero of a lot of what I talked about. And let me mention that he's very interested in doing quantum dynamics on quantum computers, which is actually the topic of a future KITP program that was just recently approved. So Maxime is very much interested in this kind of boundary that other people are interested in as well. And then, of course, there have been some very good people working in this area who passed through Berkeley in the past, and there are 3 of them. So let me stop there. Thanks.
Okay, thank you very much. Hands up, people who want to ask questions. Yes, Leonid.
Yeah, maybe just to break the ice, if there is any. Thanks. It's a wonderful talk. Lots of material covered. So I wanted to ask you, you mentioned Tamanaka-Lattinger. So again, at low temperatures, you can use bosons, you can use fermions, which are kind of interchangeable, more or less. Now, the question I have is that whether, if I start from that and raise temperature, whether KPZ sets because of collapse or lattice is not important. Do you have a feeling about that?
I mean, I think if you have, you could have an integrable field theory that would have, I think, super diffusion if it had the right properties. So I don't know that it's directly connected to Umklapp. I mean, here's my rough picture of what's happening with the Luttinger liquid picture, if you like. So you start off and, you can usually analyze the leading behavior of perturbations to the Luttinger liquid and get estimates of conductivity from like memory matrix and things like that. But there is an assumption when you do that. So I mean, this is something that a sin that I've committed, but I knew that it was applicable in some cases, so it wasn't too big a sin. You ask, well, I've got a current that would live forever in the Luttinger liquid limit, and I say, okay, well, here's a perturbation. What perturbation it is, for example, Furusaki and Matveyev is probably the classic paper on this, or at least one classic paper. You ask, what is the leading process that would cause this current to scatter? And then I assume that gives rise to an exponential decay. And I think in systems that are not integrable, that is the right picture, that the corrections to the Luttinger liquid give you unusual power laws in conductivities. You get conductivities that blow up, with the 8th power of temperature, for example, or, some power of how far you were doped or whatever. So umclap can often be the leading perturbation that causes scattering of the current. But the main point here is that picture of what the scattering does is not really correct in the integrable model, because it doesn't take you all the way to just Gibbs ensemble. There are limitations on what the scattering can do only because of integrability. So if you like, what's breaking down is the sort of memory function idea, that you can just assume that once you've got a rate, you can make that an exponential decay. So if that made sense, I think that's, that's saying that there still is a time scale for these perturbations to kick in, and you can kind of calculate, when does the Luttinger liquid behavior start to stop? It's because of those umclaps and other things. But the ultimate fate from having umclap is different in the integral model, because umclap can't thermalize you fully. Well, if you had if you had a couple of other perturbations and you destroyed the integrability, then you would get the correct answer. So in other words, I think it's fairly special cases where this is the right physics, but there is physics where all the umclap and other things that are not in the Luttinger liquid, they break the Luttinger liquid, but they give you KPZ instead of diffusion.
So what is the short answer? I mean, do you need backscattering lattice or not? What do you think? I'm not asking, for a definitive answer, but at least what was your feeling?
Well, okay, let me assume you mean by not having back. I mean, I need so I would say if I have an integrable model with a non-abelian symmetry, I can get KPZ, and there are models like that that don't even have a lattice. So in that sense, I don't need a lattice and I don't need umclap to get KPZ, is the short answer.
See, because you mentioned
shall we?
Yeah, maybe we should move on, yeah.
Yeah, sorry. Jörg?
Yeah, hi. Hi, Joel. Thanks a lot. And it was a lot of interesting things. Also might be something that might relate to some of the other experiments you do, which I'm not going to talk about afterwards. So my question is that, you talk a lot about Luttinger liquid, but I mean, there's another, nice model we can implement, which is Sine-Gordon, which is much more linked to the spin 1/2 physics, which has all these topological excitations as a gap and something like that. And it's also, we can tune basically, we can tune it to being extremely strongly correlated in the experiment. And, could you map that onto a Sine-Gordon-like model? Because many of these spin chain things can be mapped at Sine-Gordon into Sine-Gordon-like.
That's right. I think the Sine-Gordon model is integrable, and it will have this range of behaviors. And if you could get to just the right point where it has the SU2 symmetry, there is such a point, I believe, then you will get this kind of physics. I mean, the advantage of doing it in solids, I'll put it that way, is the fact that the solid is cubic has sort of put you at the isotropic point naturally.
Okay.
So all you've done by going to a solid is remove one tuning parameter that you need, but on the other hand, you've added lots of decohering things. So I think it would be fantastic to have a realization of this point with atoms. I think there would be some advantages to the atomic case if you can pull it off.
Yeah. Because, I mean, we observed something that looks like in hydrodynamics in a very, very strongly correlated, very far off equilibrium Sine-Gordon model, which looks like really time local equilibrium. Now we are completely lost in how to describe that. Yeah. But it might be some, maybe we should talk about maybe some of your hydrodynamic approximations.
Yeah, I mean, I think there are several different
type of experimental observations. Yeah.
I mean, there are different things that happen and give you nonlinear behavior, and sometimes you can get continuously variable exponents. Like if you have there are certain things in a Luttinger liquid, certain ways of driving it that a few of us worked on that will give you other ways to get power laws. So I don't really know which is the right one for your experiment. Like,
I don't know.
If you can see the unusual scaling in just linear response correlators, then it's probably something like what I talked about today. If it looks more like a strongly driven nonlinear thing, then it would be another thing that we should still talk about.
No. The question is that we have to do the linear response experiments now. That's true. But,
yeah, because I think you could divide up the cases where you get unusual power laws. There's some where it's really a linear response phenomenon like here, and there are others where at linear response it would be diffusive, but because it's strongly driven, you get something else.
Okay.
So
shall we
okay, thanks a lot.
pass the word to Mehran? Mehran, are you there?
Yes, thank you, Joel, for the very nice talk. A very brief question. Do you see any prospect of a two-dimensional system that could show dynamics like the 2D KPZ?
I don't immediately. I do think it would be very nice to take some two-dimensional crystals and analyze their neutron scattering in this way and just look for collective spin dynamics. But in other words, I don't think people have ever thought very much about this regime of low frequency, high temperature. It's usually the opposite. But I do not know a case, maybe someone else on the call does, but I don't know a case that would naturally be 2 + 1D KPZ. It'd be great to have one.
Thank you.
Can I ask a small question? I'm puzzled. There is all this enormous literature of mapping, starting from supersymmetric Yang-Mills and then calculating expectation of products of operators and then mapping this onto a spin chain, which is usually integrable and usually with larger groups, I mean non-abelian groups. What does KPZ have to say, if anything, about the original model? Shouldn't this tell you something about the model you started from?
Yes, it tells you something about correlators at high temperature in these models with non-abelian symmetries, but I don't think people had really thought to look at it. But if you like that Ilievsky et al. Paper, I think is kind of the place I might start.
Okay. Thank you very much. If there are no more questions, Jörg, it's your turn.